In the previous video, we were looking at electromagnetic induction and how an EMF is induced when a conductor moves through a magnetic field. In this video, we're going to tie that back into magnetic flux, and we'll do that by looking at Faraday's law. Now, before I jump straight into the definition for Faraday's law, we're going to sort of build it up and have a look at how Faraday's law relates to the concepts that we've been discussing, and then we'll finish off with the definition. Now, Faraday's law is best described by going back and considering that same sort of scenario that we did in the last video, but we're actually going to also add a conducting rail. So we're going to start with a conductor sliding along a conducting rail, and that's all going to be positioned in a magnetic field. So to make more sense of that, we'll have a look at a diagram, and that will help to describe the quantities that we need to consider and give you a bit more of an idea of what's happening. So we'll start off with this rail, so represented here just by a light black line, and the conductor that we're going to have is going to be positioned on top of that. So they're in contact, both made of metal and sliding along, so that we have the velocity of this conductor to the right in that orientation. The other quantity that we need to be aware of here is the length of the conductor, which is ultimately the separation of those two rails, and that will be given by L. We also need to be aware of the magnetic field that's in this region, so I'll just produce a few lines here representing the magnetic field. You'll recall that the crosses here mean that the magnetic field is going into the screen, and is uniform given that these crosses are evenly spaced, and we're going to make sure that this field is spread across this whole region so that the conductor is moving through that uniform field at a constant velocity. So that's the starting point that we're going to look at, and we need to consider what happens when that conductor has moved to the right at some later point in time. So it might be positioned, say, over here somewhere. I'll just draw that in as a bit of a dashed line to represent the location of that conductor. Now, we know from the previous video that the charges are going to separate, and you can use the right hand palm rule to identify that the top of this conductor is going to be positive and the bottom is going to be negative. Now, I'm only going to indicate a plus at the top and a minus at the bottom, but keep in mind here there would be a whole stack of positive charges pushed upwards and a whole stack of negative charges that would be pushed down. And the reason for that, as we saw, is that the magnetic force causes those charges to be separated. And just to reiterate, that magnetic force, we can identify the equation that would give us the size of that force. So that magnetic force is given by the equation F, and I'm going to use a subscript B here, would be equal to QVB. So Q being the size of the charge, V being the velocity of the conductor through the field, and B being the magnetic field strength or the magnetic flux density. What I didn't mention in the last video though is that with that charge separation, we've actually now got a build-up of positive charge at one end and a build-up of negative charge at the other. So there's actually also going to be an electrostatic force of attraction between those charges. So that electrostatic force is going to result from purely the separation of charge, and we know that opposite charges attract. So there is an electrostatic force of attraction that also exists here. And that force is given by the equation Fe is equal to Q times E, being the electric field strength. Those two forces in this scenario are going to be balanced. So with the charge separation due to the magnetic force, we're going to see an electrostatic force that is equal and opposite to the magnetic force. So that means that we can equate those two forces. So we can say that FB is equal but opposite to Fe. Now, if we make those substitutions, we can see that QVB is going to be equal to QE. Now, I should mention here, this derivation that I'm going through, you don't need to reproduce it. I think it's just really helpful to identify how the equations for Faraday's law come about, rather than just throwing them in front of you. The next step in this derivation, though, is to identify that the charge is going to cancel, given that it's the same on both sides. And we can also identify that the electric field strength is given by the equation E is equal to V on D. That's a capital V representing voltage, and D being the distance between the ends of the electric field. But we can also identify here that that value of V is actually going to be the EMF that's generated between the ends of the conductor, and the value D is simply the length of the conductor, given that that electric field will be established through the conductor itself. So substituting into that equation now, you have that VB is going to be equal to negative EMF over L. And rearranging to calculate EMF, we can show that EMF is going to be equal to negative B LV. So there's the equation that we can use for a conductor moving through a magnetic field. You'll notice that I'm not highlighting that one. It's not actually in the syllabus. There's another derivation that we need to follow through now to show Faraday's law as stated in the syllabus. And to do that, we're going to have a look back at that diagram to consider one particular aspect. And that is the fact that when we're looking at the velocity here, we can identify that once the conductor has moved from position A to position B, we're going to see that the conductor has moved through a distance. We're going to call that distance delta S, so the change in the displacement of the conductor. And at point B, that's going to be a time, some delta T, after it was positioned at point A. So you notice there we now have delta S and delta T. We can then relate that back to the velocity of the conductor itself. So we can say that V is actually equal to delta S over delta T. Making that substitution, we can therefore say that EMF is equal to negative B L delta S on delta T. And we're going to use a few more algebraic steps here. The first being if we consider the product of L and delta S, so we've got a length multiplied by a change in distance, so two distances being multiplied together, what we effectively have there is a change in area. We're really now looking at how the area changes rather than just considering the velocity itself. So substituting that into the equation, we end up with EMF is equal to negative B delta A on delta T. Remember that flux is equal to B times A, and considering here that we have B being multiplied by delta A, we can therefore say that we're looking at a change in flux given by B multiplied by delta A. So to make that substitution, we come to the next step, being that EMF is equal to negative delta phi on delta T. So notice here that we now have a rate of change of flux. So we're looking at what happens with the flux, how it's changing, in order to determine what the EMF is. There's one more small step that we need to consider, and that's the case that this particular equation only applies for a single loop. So in the diagram above we had one single loop through which current could flow, but we need to consider a situation where multiple loops can be involved. And so if we had multiple loops, all we need to do is multiply that by the number of loops. So that means we have the equation EMF is equal to negative N delta phi on delta T. And this is one of the equations that you'll find in the data booklet, where EMF is simply the electromotive force that's induced in this particular case. And the units of electromotive force, as we've seen, are volts. N is the number of loops. and delta phi on delta t is the rate of change of magnetic flux. Now we need to look at that idea in a little bit more detail, given that the rate of change of magnetic flux can be caused in a number of different ways. And let's just delve into that in a little bit more detail, and that will develop a second equation related to Faraday's law. So we can identify that delta phi can change due to three particular circumstances. In some cases it might be more than one occurring at one time, but we're mostly going to deal with only one change at a time. So that change could be due to a change in the magnitude of the magnetic flux density, so I'll represent that as the magnitude of B. It could also be affected by the direction of the magnetic field, or it could be affected by the size of the area. So that means that we can express delta phi as being equal to the change in the equation for phi being B A cos theta. So we can have a change in any of those quantities and even a change in the direction of B. That we're going to simplify in one further step, representing it as B multiplied by the perpendicular area. I'll explain what that is in a second, but ultimately we're now going to substitute that into the previous equation to show an alternative version of Faraday's law where EMF is equal to negative N delta B multiplied by the perpendicular area over delta T. Now the way to think about this value of A, I'm representing it this way given that that's how it's represented in the data booklet, is the area component that is perpendicular to the field. So it's a little bit of an unusual one. Ultimately it comes back to that cos theta term and incorporates that cos theta term to calculate the change of flux that's perpendicular to the area. And as I said, this equation is also in the data booklet. So this one highlights a little bit more clearly that the EMF can be induced due to a change in the magnetic field strength, a change in the direction of the magnetic field, or a change in the area. So now that we've gone through all of the derivation to get to those two equations, let's have a look at the definition for Faraday's law. And again, as always, this is from the glossary. Faraday's law is a law stating that when the magnetic flux, and again notice here that we're now talking about magnetic flux as being the reason why we have an EMF being induced, that magnetic flux is linking a circuit. So we're dealing with a situation now where a current will flow, and when there is a change in that magnetic flux, an electromotive force, otherwise known as a voltage, that will be induced in the circuit. And the size of that EMF is proportional to the rate of change of flux linkage. Now, the term flux linkage is not one that we need to go through in any significant detail, but to provide a little bit more scope to it, you can think of flux linkage as simply being the product of the number of loops and the flux that's passing through each loop, so N times phi. So if you go back to those equations, we had N delta phi being the flux linkage, and so the rate of change of flux linkage is N delta phi on delta T. Now, you might have noticed that there was a negative in that equation. We're going to deal with that in more detail in the next video when we look at Lenz's law.